arrangements. And find zonotopal tilings. And I don't think I stated this officially, but stretchable pseudo-line arrangement is stretchable if and only if the corresponding zonotopal tiling is regular. So and sometimes, yeah, for two-dimensional pictures, it's usually easier to decide whether you can draw something with straight lines than. I mean, for regular, you have to go through all possible vectors, all possible assignments of heights to your vectors, and that's trickier to do. Yeah, and today I want to sort of continue my analogy between tilings and triangulations. So what I want to do today is flips of fine zonotopal tilings. And yeah, I think I mentioned it before, but let me do this sort of properly. So I'm going to assume they have a vector configuration in RD. And I'm going to assume that these are in general position. Which means that, any, at most, D vectors are linearly independent. And OK, so now I want to take the zonotope and ask how many fine zonotopal tilings. So let's say when n is equal to D, then how does the zonotope look like? Simplex. Actually, parallelepiped. OK, nice. Yeah. So it's it looks sort of like a cube, or I mean, it's a finely isomorphic to cube. And so how many fine zonotopal tilings does this polytope have? 1. Unique fine or not zonotopal tiling. OK. Now, what about n equals to D plus 1? In which case, yeah, so in which case V is what I would call a circuit, which for vector configurations means that it's a minimal linearly dependent set of vectors. For point configurations, we had minimal affinely dependent set of vectors. Here it's linearly dependent, which is consistent with the fact that you can, with the correspondence I mentioned between point configurations and vector configurations. So how many fine zonotopal tilings of the zonotope in this case? Should be 2. Yeah, and that's actually true. For a hexagon, that's true. OK, so in the hexagon is the Minkowski sum of 3 vectors in R2, and it has exactly 2 flips. So when you hear the word flip for zonotopal tilings, you should immediately think of this picture. This is a flip. This is a typical flip of zonotopal tilings. And yeah, so but this holds in arbitrary dimensions. So this example, when n is 3 and d is 2. Turns out that this zonotope has exactly two fine zonotopal tilings. And we're going to say that these two tilings differ by a flip. So maybe I should, so this is n equals 3, d equals to 2. Maybe another example would be n equals to 2, d equals to 1. Then what's my zonotope and what are the two tilings? A line. Is it like a whole line or a line segment? Okay. The tilings are what? The arrow or the? Well, I see. So well, okay. So let's actually see. So it's a sum of two line segments in R1. I have one line segment, and I have another longer one, and then I get a very long line segment with an extra point. So yeah, the two fine zonotopal tilings actually two fine zonotopal tilings. Maybe this is V1 and this is V2. So how do they look like? Yeah. Nice. Okay, right. So they have to be fine. So for triangulations, right, remember we had like either the whole line segment or these two line segments together. So like you either include the extra point or you exclude. But for zonotopal tilings, it's different. So they look like, indeed, either V, this is V2 and this is V1, or V1 and then V2. So this is a flip. You kind of swap two. All right, how about another example where example n equals to 4 and d equals to 3. Remember, I drew all these three-dimensional pictures for flips of triangulations, right? So here you should take 4 line segments in 4. I mean, you kind of imagine the plane here, and then you take 4 different vectors in R3. And then you take the Minkowski sum. So how's this polytope going to look like? That's actually tricky. Yeah, it looks like a, well, yeah, like a projection of a 4-dimensional hypercube. Let me actually show you. I should be able to do this. No, doesn't work. Let's see what's going to happen. Maybe that nothing happens. Nothing happens. Yeah. Oh, it's happening. All right, nice. Yeah. Okay. So the whole polytope looks like this, and then the flip consists of replacing 4 little cubes with 4 other little cubes. Yeah, and I guess it's a little bit too fast. Yeah. Yeah, I think it's the only GIF I have ever created, or one of the two. Yeah, anyway, so the kind of, there is, yeah, I guess you can try to memorize what happens here, or yeah, if you want a slower picture, I can send you later. But yeah, so that's basically a flip is you replace these 4 little cubes with these 4 little cubes. Which, yeah, by the way, you can find this picture on my webpage. Just Google my name and press gallery. Picture webpage. And so you always, I mean, you get almost the same sort of story as for triangulations, right? And yeah, so same story for zonotopal tilings, namely, well, you can ask, like, you can consider the set of all fine zonotopal tilings. And you can ask, well, are they all connected by flips? And what is the answer? Nobody knows. Hmm? Yes. Hmm? You don't know. Nobody. Yeah. Yeah. The answer is no. So when I mean the same story, I mean that. So for triangulations, we had examples where there are triangulations which have no flips. Same thing happens here. So there exists fine zonotopal tilings with no flips available, but these are very hard to construct. And also, if you only look at the regular fine zonotopal tilings, then they have a very nice structure. There exists a polytope, which is called the fiber zonotope. And so its vertices, whose vertices correspond to regular fine zonotopal tilings and whose edges correspond to flips and whose dimension is n minus d. So it's sort of like the secondary polytope, but except it's a zonotope. I mean, this polytope actually also happens to be a zonotope. It's sort of curious. And you may wonder, why are these two stories so similar? Should there be a common generalization of stories? And in fact, there is. And I'm not gonna explain any of it, but let me just mention. I think this is pretty cool. So, oh, by the way, I should mention, okay, before I tell you about the generalization, let me mention what happens in general when d is equal to 1. When d is equal to 1, my zonotope is a sum, Minkowski sum of a bunch of line segments. What is the, how many fine zonotopal tilings does this have? N factorial, nice. N factorial fine zonotopal tilings. What do the edges correspond to? What do the flips correspond to? Swap in adjacent segments. That's true. So what is this polytope? What is the fiber zonotope? Right. It's so in this case the fiber zonotope is the permutahedron. Well, it's combinatorially equivalent. So somehow, which by the way is a zonotope. So yeah, and there's a very general story, which is, yeah, in general, these fiber zonotopes, I mean, the permutahedron is the Minkowski sum of hypersimplices, and the fiber zonotope, there's actually something called higher secondary polytopes, which we came up with Alex Plotnikov and Lauren Williams, and actually, each fiber zonotope is also a Minkowski sum of a bunch of higher secondary polytopes. But anyway, let me now mention the general story. So general the general story is the following. What is a polytope? What is a polytope? Or more generally, what is a point configuration? Well, let's say I have a point configuration. A1, 2, etc. an in r to the d minus 1. Well, the corresponding polytope is a projection of a simplex, right? So there is a projection. You can take the n minus 1 dimensional simplex, which is the convex hull of E1 up to En in r to the n. And you can project this guy to the convex hull of A, which is the convex hull of A1, An in Rd. And how do you project? You send E1 to A1 and E2 to A2 and etc. There's a unique projection of a simplex onto any point configuration like this. Similarly, what is a zonotope? We have a vector configuration, V1, Vn in Rd. Then instead of taking the simplex here, you take a cube. Take an n-dimensional hypercube, which is a Minkowski sum of these line segments here in Rn, and then you project onto the zonotope, which is the Minkowski sum of these vectors here. And indeed, again, there is a projection pi which sends E1 to V1 all the way up to En to Vn. And yeah, so as you remember, here we have triangulations, here we have zonotopal tilings. These have sort of different definitions, but the whole story is similar. And actually, the general story is that if you have any projection of two polytopes, right? This is a projection of polytopes, this is a projection of polytopes, then there is a notion of sort of pi-induced subdivision of Q, which generalized triangulations and zonotopal tilings. And there is a notion of a fiber polytope, which simultaneously generalizes fiber zonotopes and secondary polytopes. So yeah, this is all due to Villera and Sturmfels in '92. So yeah, so that's the sort of the general picture you should have in mind, is that for any projection you get nice analogs of triangulations and zonotopal tilings. But that is not studied as much as these two cases. So these two cases are, yeah? All right. Yeah. So yeah, and you can kind of think of, so what is a zonotopal tiling here? You have these zonotopes which are labeled by pairs of subsets, and actually these naturally label faces of the cube. So zonotopal tiling is actually a certain subset of faces of the cube which projects bijectively onto the zonotope here. Similarly, for the simplex, a triangulation is actually a collection of faces of this bigger simplex here, which projects isomorphically onto the convex hull of A. And so that's sort of, in general, you can take collections of faces of P, which are the subposets which project onto Q. Yeah, you can, well, I mean, yes, you can take a point here, and then you can look at the fiber over this point, and you can kind of choose maximal, minimal faces of that project, of the pre-image. Yeah, anyways, there's a whole construction here. Right, any questions on this stuff? No questions. And Yeah, so I am not yet done with zonotopes. One other thing I want to talk about is, I guess, volumes. Volumes of zonotopes. And for that, I need to introduce some terminology. So this is matroidal terminology. So let's say I have an arbitrary vector configuration. V1 all the way up to Vn. Doesn't have to be generic anymore. And what I want to define is, previously I talked about circuits, but now let me define independent sets and bases of my vector configuration. So by definition, a set I of integers of these labels of vectors is an independent set if the corresponding vectors are linearly independent. And similarly, it's called the basis of V if the corresponding vectors form a basis. So, and I'm going to denote, I'm going to use notation. So fancy I of V is the set of independent sets of V, and fancy B of V is the set of bases. Yeah. Of R to the D. Well, should I assume? Yeah, let me assume. Let me always assume that the span. Yeah, that's a good question. The span of V is just the whole R to the D. R to the D. Okay. So what do these have to do with zonotopes? Any guess? What would these notions have to do with zonotopes? I mean, I can start stating a theorem. Any guess what this is going to say? Okay, let me show you the first line. Let C be a fine zonotopal tiling of my zonotope. Then there's going to be 1 and 2. All right, last call. Okay, so the first claim is that the top dimensional tiles of C are in bijection with set of bases of V. This is one claim, and another claim is that another claim is going to be about independent sets. What is something is in bijection with independent sets. Tiles. No. Well, I mean, not all tiles. Yeah, let me actually try an example, maybe. Let me try an example. Let's say I draw a picture like this. Okay, so my vector configuration V is a configuration of 4 vectors like this. And if I count the top dimensional tiles, 1, 2, 3, 4, 5, 6, is 6, which any two vectors form a basis. So this number of bases of V is also 6. If I want to count the number of independent sets, how many independent sets? Hmm? 11. Nice. Yeah, so there is one empty set plus 4 one element sets plus 6 bases. That's 11. What is 11 about this picture? All right, let me. Basis under parallel translation. That's actually okay. You're rephrasing the notion of an independent set. That's actually okay. Let me tell you. Number of vertices. The vertices of C are in bijection. With the independent sets of V. So I guess I didn't draw the vertices. For some reason, there is 11 vertices here, and you can try, like, even in 2 dimensions, you can try checking this theorem. So let me do one more example, or maybe, I mean, I can choose some other collection of vectors. V1, V2, V3, maybe V4 is just zero vector. And then my zonotope. I can choose a zonotopal tiling, I guess. I mean, this example is sort of easy. Here's an example of a fine zonotopal tiling, right? This is V3, V1, V2. So I get 2 top-dimensional tiles. This is a random example. I don't have it in the lecture notes. Okay, so I just hopefully there's 2 bases. Okay, there's 2 bases. How many vertices? 6. 6 vertices. How many independent sets? Indeed 6. Size of the independent sets is 1 plus 3, right? Because the V4 doesn't count. Plus 2. Okay. Seems to work. And actually, yeah, it works in all dimensions. Okay. And how do you prove this result? Okay, so you want to find an explicit bijection, and actually, I see. Well, I mean, yeah, that's what we're supposed to do. Just guess. Actually, for the first part, there is an easy bijection, which proof idea. For the first part, you just explicit bijection, which, so you have a fine zonotopal tiling C, right? And you have some top-dimensional tile Zij in C, which, remember, Vij is the sum of line segments from 0 to Vi for I and I, shifted by sum of over J and J of just Vj. And the idea is that, so this is a top-dimensional tile if and only if I is a basis. And the claim here is that you just map the Zij to I. I is a basis. And the claim is that this is a bijection. Yeah, that's a great question. How do we know we don't get multiple copies? And somehow that is true. I mean, yeah, so the bijection is easy to write down, but it's hard to show that it's a bijection. And so the fact the example where this happens is if all your vectors are in 2 dimensions and they are all, if they are all generic, right, then a zonotope is going to be like a convex 2 and gone. And if I draw the corresponding dual to the line arrangement, also known as the subway map of St. Petersburg. So what I'm going to see is that, so if V is generic in 2 dimensions, then any 2 pseudo lines intersect exactly once. Any 2 pseudo lines intersect exactly once. So in particular, each pseudo line, so the right pseudo line it connects all these vertical vectors together. And so this vertical vector appears in the tile with each other vector in your vector configuration. So the fact that any 2 pseudo lines in this case intersect exactly once explains why every 2-dimensional basis appears exactly there is no repetitions for each given basis I. Yeah, but what happens in general? Like in this example here, I have V1 and V3, and then V2 and V3. So the 2 bases appear exactly without repetitions. And this is completely, like even in 2 dimensions, this is not completely obvious. And this is true. And for 2, the explicit bijection is harder to construct, but the actual proof of both of these things is by using the deletion contraction recurrence. Deletion contraction recurrence. You may have seen this for graphs. I'm not going to tell you yet what this means for vector configurations. You can try to guess. It's pretty natural construction, but we're going to later study this for matroids and hyperplane arrangements. So basically, you can prove both of these by induction. So choose the vector, and then you can contract the vector, or you can you can sort of project onto its orthogonal complement, or you can remove the vector, and somehow these two operations together they interact very nicely with zonotopal tilings. So that's sort of the proof idea. Yeah, I think I'm gonna explain this later in full detail. Any questions so far? Okay. Let me actually leave the theorem. Okay, corollary. Corollary, which is originally a result due to Macmillan question. I don't know what the year, nobody knows the year, but the first time it appeared in the literature is trafford 74 is an expression for the volume of a zonotope. Volume of a given zonotope for a given vector configuration is, well, what do we know? We know that the top-dimensional tiles of any zonotopal tiling are in bijection with bases. So, and it's easy to compute the volume of each of them. Sum determinant. So it's a sum over all bases, right? So it's, and we'll just write it like this: I1 less than I2, etc. less than I p and n. And then I'm just going to take the absolute value of the determinant of vi1 of the matrix with columns vi1, vi2, all the way up to vid. Okay. So, or like the order polytopes, we computed the volume using triangulations, by triangulating into simplices. Here we're subdividing it into these fine zonotopal tiles. And so that's basically, I mean, is it clear why this is true, or should I write it? Okay, this is clear. And one particularly nice example where this works very well is when each determinant is equal to 1. Or, I mean, each non-zero determinant is equal to 1. So let me make a definition that a vector configuration in RD is unimodular if, so what I want to say is that if each vi is an integer vector, and yeah, this is not necessary for the volumes, but later I'm going to talk about lattice points, and this is going to be necessary. And for each basis I, the determinant of the corresponding vectors is equal to plus or minus 1. Which arrangement is equivalent? Yeah, that's actually not true, right? I mean, yeah, you can't really, if you have a vector configuration like this, you can't, like this basis here has volume 1, and the other basis has volume 2. If you apply any affine map, this is still going to be true. I mean, affine maps don't really change the ratios of bases. But yeah, this condition is basically saying that every basis has the same volume, the parallelepiped spanned by it. Any other questions? So this unimodular condition is useful for us as combinatorialists because we don't have to compute determinants anymore. We can just compute the number. In this case, let me actually state this as a proposition. So, proposition. If your vector configuration is unimodular, then one is not surprising statement is that the volume of the corresponding zonotope is just the number of bases. And the other one is pretty unexpected, is that the number of lattice points, so not the number of points in your zonotope with integer coordinates is just equal to the number of independent sets of your vector configuration. So in other words, this means, remember the right-hand side here is number of vertices of any fine zonotopal tiling. And if all vectors are integers, then all of those vertices are going to be also going to have integer coordinates. So for any fine zonotopal tiling, its vertices are contained inside this set, but actually the claim is that if it's unimodular, then you get all lattice points as vertices of any fine zonotopal tiling. Yeah, if it's unimodular, you never get a lattice point inside a fine tile of a this is, I want each vector to be integer, and I'm taking a specific zonotope, right, which is just the Minkowski sum of line segments from the origin to each of these vectors. So this is not the translation invariant notion. Oh, you're asking if a unimodular vector configuration exists for all n and t. That's actually true. I'm going to give you an example. Well, I mean, if you want many vectors in a low-dimensional space, well, actually, I need to think maybe if you take too many, you get in trouble. But you can take quite a lot. And let me now apply this proposition to a particular nice example of zonotopes, namely graphical zonotopes. Corollary if G is a graph, then what is the volume of the corresponding zonotope? Remember, we had this graphical zonotope. Did I remind you? Okay, so if G is a graph, and you label the vertices by bracket n, then the corresponding you can look at the vector configuration. Well, you can take the corresponding zonotope, which is the sum of these line segments from EI to EJ, where I and J is an edge. Or you can rewrite this sum to be of that form over there, and you still get integer vectors. So yeah, the claim is that for any graph, the volume is just the number of spanning trees of G, and the number of lattice points is the number of forests of G. And well, I have to prove it, right? And the proof is actually sort of annoying. Yeah, a forest is an acyclic subgraph of a tree is a connected, a spanning tree is an acyclic connected subgraph, and the forest is just arbitrary subgraph, has to use all the vertices of my graph, but other than that is spanning forest. Thanks. So why is the proof annoying? One reason is that the actual volume is 0. The zonotope lives inside an n-1 dimensional space. I should maybe n-1 dimensional volume. And what do I mean even by an n-1 dimensional volume of a polytope in R to the n? That's all easy but annoying. So let me do this properly. So whenever you have a polytope which has one dimensional lower than you need, what you do is you just project. You just forget the last coordinate, all points. Project from Rn to R n minus 1 by forgetting the last coordinate. And note that actually, well, it is not true that here this polytope has the constant last coordinate. I mean, it lies in the space where the sum of all coordinates is, right, it's d sub g is the subset of x in Rn, sum of xi is 0. And this version of, well, not exactly. I could take an orthogonal projection onto this hyperplane, but instead I'm doing something weird and different. I'm removing the last coordinate. This is different, right? It's not an orthogonal. The image is a different hyperplane. And the reason I'm doing this is because, first of all, it's easy to say what happens to volumes. If you have a unit cube here of volume 1, it projects down onto a unit square here of volume 1. And if you have an integer lattice point here, it sort of projects onto an integer lattice point, and it's actually, I mean, if you have an element in this hyperplane, and if you know that all of these n minus 1 points are integers, then you know that the last coordinate is also going to be an integer. So somehow this projection is the standard thing to do. It's very convenient to work with. But at first, it may seem counterintuitive. Yeah. So now, yeah, if I want to describe the basis, if V is my vector configuration of this form, so EI minus EJ, where I and J form an edge. If I take this vector configuration, then the corresponding vectors in V form a basis of, yeah, I have to project V down onto R to the n minus 1. Of R to the n minus 1. This happens if and only if the corresponding edges form a spanning tree. Okay, and that is some exercise, right? So you have to write down some determinant and make sure that there's a unique, yeah, moreover, V is unimodular. For any spanning tree, the determinant you get is equal to plus or minus 1. And that's it. Basically, after that, you're done by this corollary. Independent sets correspond to spanning forests, which are subsets of spanning trees. Yeah, so basically that's the whole proof. Yeah, and I'm out of time. Any questions? All right, yeah, I'm out of time, so have a good weekend, everybody. See you all on Monday, I think. Yeah, Monday.